All right, they're asking for the interval of convergence for the series representing f prime, f double prime, and the integral of f of x dx. So the first thing to do is to find the endpoints because the endpoints are the same for every series. We'll use the ratio test, which tells us that the series will converge when the limit of the absolute value of the n plus 1 term divided by the nth term is less than 1. So let's find out for which x values is this less than 1. So changing the order around a little bit allows us to deduce that as n approaches infinity, the red ratio approaches 1. The blue ratio simplifies to x minus 5 to the 1 power, and the yellow ratio simplifies to 5 in the denominator. So this is true when simply the absolute value of x minus 5 over 5 is less than 1. Remember, this means its distance away from 0 is less than 1, so it must be between negative 1 and 1. Therefore, x minus 5 is between negative 5 and 5. So the values of x for which our series converges are definitely between 0 and 10. And now to check the endpoints. But before we do, a quick note that your communication should have identified that you use a ratio test, and it should have communicated that your series converges if this limit was less than 1. So make sure to communicate this black part and this green part in front of the limit. A lot of students often leave that out, and their work is incomplete. So the series for f of x is already given. The series for f prime of x, using the power rule, n times the coefficient times x minus 5 to the n minus 1, all over n times 5 to the n. Remember the expression, like for example in the denominator with n's, is just a constant. It's just part of the coefficient. The only variable we're taking the derivative with respect to is x. All right, in the second derivative, again, this stuff is all just constant. So we have this base with x to the n minus 1 power. The derivative will be the power times the base to the power minus 1. So there's our series for the second derivative. And then our series for the integral. Let's not forget, right out of the gate, the constant. And then the series will be the antiderivative of each term of f. And each term of f has x minus 5 to the nth. So here we're going to have x minus 5 to the n plus 1. Which means if you went backwards and took the derivative, you would have n plus 1 times x minus 5 to the nth. And we need that n plus 1 to factor out because it's not in the numerator. So the constant n, 5 to the n, is still down there. And now we have our series for f, f prime, f double prime, and the antiderivative. For each of these, the interval of convergence goes from 0 to 10. But for each of these, we don't know if the series converges at 0 and or at 10. So we'll not need to check the endpoints for every one of these. How do we do that? We just substitute this x value in for x and see if the new series converges or diverges when x is that endpoint value. Let's begin. Oh, quick note, everything here is fine. However, we could change the index of summation, or the summations index on one of these. Let's look at the first function. When n is 1, we have an x minus 5 to the 1th power. For the first derivative, when n is 1, we'll have x minus 5 to the 0 power, which is 1. So we just have n over n to the 5n. We can cancel out those n's. And again, when n is 1, we have 1 over 5. When we take the second derivative, that first term was just a fifth. And when we take the derivative, it'll be 0. So when n is 1, our first term here is going to be 0. So we can leave it as 1, but since it's a 0 term, if we want it to begin with a non-zero term, we can change that to 2. And again, these n's cancel out, which I didn't simplify that earlier, but we can do that now. All right, so not absolutely necessary, but you'll see it a lot, so that there's no 0 terms when you expand the series. All right, let's substitute 0 and 10 in for x for each of these series. All right, if x is 0, we have 0 minus 5, which is a negative 5, which you should think of as a negative 1 times 5. Now that's raised to the nth power, so the negative 1 to the nth power times negative 1 to the n plus 1 power. Add the exponents, and you get negative 1 to the 2n plus 1 power. The 5 to the n and the 5 to the n cancel out. This exponent is always odd, so this is not alternating. This is just negative 1 over n, which is essentially the harmonic series, the opposite of the harmonic series, which diverges. So f does not converge at the endpoint 0. And when x is equal to 10, then we have 10 minus 5, which is positive 5 to the n. This is an alternating series, and this is the alternating harmonic series, which we know converges. So f's interval of convergence is half closed, half open. All right, we'll do the same thing for the derivative, the second derivative, and the integral. This will be fast. So by substituting in x equals 0 and 10 into each of these, we get these 6 series. These 4 all diverge by the nth term test for divergence. This series diverges. We could use the limit comparison test versus the diverging harmonic series. And this series converges. We could use the ratio test or the direct or limit comparison test versus the converging alternating harmonic series. Therefore, our intervals of convergence for the series for f prime, f double prime, and the integral of f dx are the half closed, half open for f, the open interval for f prime and double prime, and the half closed, half open interval of convergence for the integral of f of x dx. All right, this video is a little long, but there's a lot of work to do. I hope this helped.